All right, hi guys. So let me see. I think I'm gonna go ahead and put up a relatively straightforward exercise for you guys to work on, kind of as a warm up, and then after that, I'll take some questions if you have them, and I mean obviously I have some more problems that we can work on too, and then I'll try to figure out like how to like fit everything in what order to do stuff. So let's see. So for the first little warm up here, let's do this one. So suppose f is continuous on 0, 2, and f of 0 equals f of 2. Prove there exists xy in 0, 0, 2 such that y minus x equals 1 exactly, and f of x equals f of y. And yeah, well, the book gives a hint here. I guess I'll go ahead and just give the hint. So consider g of x equals f of x plus 1 minus f of x on 0, 1. Okay. Yeah, so this is the warm up. And then, like I said, after this, so let's take maybe 5-ish minutes, 7 minutes maybe. So let's resume. We'll resume. Oops. At 5:15, and then, like I said, I'll be happy to take questions, and I do have more problems picked out for us to look at. So, yeah, we'll take it from there. Okay, so let's go ahead and just go over this real quick. So this one is supposed to be, it's sort of like one of these questions where it's kind of like a cute application of the intermediate value theorem, right? So it's like you get this like auxiliary function where basically applying, in the end, like applying the intermediate value theorem to this auxiliary function somehow gives you the result that you want, right? So the idea is like, okay, so either, right, either like basically you want to apply the intermediate value theorem to G using like x equals 0 and x equals 1, right? Because it's like if G, like for example, if G was like positive at x equals 0 and then like negative at x equals 1, then there would have to be a place where G was 0 in between. And if G is 0, then like x and x plus 1 are the points x and y that you're looking for. The only like weird situation is if G happens to be 0 at both x equals 0 and x equals 1. But if that's the case, then yeah, or actually if G is 0 at either one of them, sorry. But if G is 0 at either one of them, then you automatically get like the x values that you want, right? So either G of 0, like so basically you can do like just a couple cases. So case 1, G of 0 and G of 1 are like, let's see, wait. Are, is that right? 0 equals that. Oh, right, because f of 0 equals f of 2. That's right, okay. So if G of 0 and G of 1 are both, yeah, I forgot about this f of 0 equals f of 2 thing. If G of 0 and G of 1 are both non-zero, right, then you can say that suppose that loss of generality that G of 0 is greater than 0, then that means that f of 1 is greater than f of 0. Oops. Since f of 0 equals f of 2, this means G, so f of 1 is like greater than f of 2. So G of 1 is negative. Then the intermediate value theorem says that G of x equals 0 for some x in 0, 1, right? And then x and x plus 1 are the desired points, right? Because if G of x is 0, then that means that f of x equals f of x plus 1, which is exactly what we want, right? And then on the other hand, one of them could be 0, right? But then it's like obvious, you know, so like case 2, 1 is 0. Like without loss of generality, say G of 0 is 0. And the only reason I can say without loss of generality, like honestly, it's almost an abuse of the term without loss of generality, because like, you know, normally without loss of generality, you only apply when you're saying like you can basically rename some variables to make your assumptions be true, right? And that's not actually the case here. It's more like by symmetry. Like, okay, maybe I should say like this, like by some, or yeah, I don't know. It doesn't, I don't know. I'm being sort of too technical about this. Let's just say g of 0 is 0, then like f of 0 equals f of 1. Oops. So we can take x equals 0, y equals 1. And then like g of 1 equals 0. Similar, right? You can take x equals 1 and y equals 2. So that's kind of what I was really trying to say. It's probably, without loss of generality, it's like technically not, it's not good to be in the habit of just like saying that whenever you're trying to say that like you can reduce to a particular case or something. Yeah. Here, definitely, like, it's also still slightly abusive, but it's less abusive in the other one. It's more okay to say without loss of generality here, because at least you can just like, you could replace g with negative g or something, right, to get this to be true. So, all right. Anyway, sorry. I have a weird like tick about people misusing without loss of generality, because it happens a lot. All right. Anyway, so that's it for this problem. Any questions about the problem?
Question?
Yeah.
Wouldn't it be easier to just like say, okay, g of 0 is f of 1 minus f of 0, g of 1 is f of 2 minus f of 1, and so you just add them up and you get that g of 1 plus g of 0 is 0. So you know that g of 0 is negative g of 1. So that means one of them has to be negative if the other is positive. And then,
Sure.
or they're both 0. I think it's pretty much the same thing that way you did. I just thought it was easier to follow that way.
Yeah, sure. That's fine. Yeah. Any other questions about the exercise? Okay. So I think now let's go ahead and I'll open it up for general questions. And yeah, also, just since there are like a little bit more people here than normal, if you can try to use the hand raising thing when you want to ask a question, that would probably be best, so that way people aren't like talking over each other and stuff. But what I was thinking we can do is, like, if you have questions, I can kind of try to like write them all down, and then we can like I'll try to like organize how we go through everything. Or if you have requests or something. Yeah, Sagar. Yeah, do you have a question?
I was muted, sorry.
Oh, okay.
In the proof, like we had the two definitions of connectedness, and then we showed the equivalence of those two definitions. There was like one thing that I wasn't super sure about, where like in the video you kind of just like used the like closure term, like kind of like intuitively. Like, could you maybe go through that proof quickly one more time?
Yeah, let's see. So hold on. Okay. Yeah, so rehash the proof here. Yeah, I'll keep that in mind. I mean, I will try to get to that, but yeah. So before I do anything, like I said, I'd like to try to like just accumulate all of the questions that you have, at least right now. Obviously, if you have more as we go on, that's also fine. Any other questions? Okay. So, all right. In that case, then, hold on. Let me do something. Huh. Oh, that's weird. Okay. Well, okay. All right. Yeah, I guess I'll go ahead and just go through this right now, since that seems to be the only question right now. So, okay. Also, can everyone just make sure that you're muted? Let's see. So, right. So the first, there's sort of two directions here, right? So, um, all right. So suppose there exist, um, you know, U1 and U2. Such that they disconnect. Well, yeah, I'm just going to say disconnecting set E, right? So then we want to show that E can be written as the union of two sets, two disjoint sets, disjoint and non-empty sets A and B, such that A inverse, oops, not inverse, closure, A closure intersect B is empty, and B closure intersect A is empty, right? So the idea is that basically A and B are just the pieces of E that are like in U1 and U2, right? So we set A equal to B intersect U1, and B is E intersect U, whoops, U2, right? And then, so clearly A and B are disjoint and non-empty, just because U1 and U2 disconnect E. I mean, that's just like that's directly like two of the requirements, right? For U1 and U2. If they disconnect E, then E intersect U1 has to be non-empty, E intersect U2 has to be non-empty, and the intersection of those two sets has to be empty, right? So that much is fine. So now we just have to show that like this is true. So in this case, it's definitely like a without loss of generality thing where we can argue by contradiction to say like, suppose for like contradiction, there was some X in the closure of A intersect B, right? So then, all right, let's see. So they call it, okay, right. Sorry. They call it B. Try to stick to their notation, right? So since B is a subset of U2, right? So little b is in U2. And since U2 is open, that means that there exists some R greater than 0 such that the ball of radius R around little b is a subset of U2, right? And then on the other hand, since B is in the closure of A, and I think this might be what you were asking about. There's a so there exists an A in A such that the distance between A and B is less than R, right? This is basically, so I mean, this just comes from proposition 13.
So is that contradicting the fact that they're disjoint then?
Yeah, I mean, well, eventually, so, okay, right. Yeah, because so that means that A, so like A is in this ball, right? So A, that means A is in, right, yeah, so that means A is in A and A is in U2. But since A is in A, that means that A is in U1. So like A is in U1 intersect U2, which is not allowed, right? So yeah, it's just the fact that this A exists that comes from proposition 13.9. So like, okay, let's see. Let me make sure that this is like clear why it comes from 13.9. Right, okay. So 13.9c, right? So what are we saying? We're saying that, okay, B is in a closure means that, and like, yeah, and R is greater than 0. We're saying we claim that this means that there exists an A in A. In fact, actually, I don't even know why they cite 13.9c. Okay, I mean, you can use 13.9c, but there's actually an easier way to like see why this is true, such that okay, why is this true? Well, suppose this were not true. Then that means that BR of B is a subset of S, the complement of A, right? But then, yeah, so, right. This means that the complement of this ball, right? Or sorry, what am I saying? That means that, right, B is interior to, right, to, yeah. So B is, yeah. And then like S minus the interior of the complement, right? Is that what I want? Is a closed set containing A. So B is in and this is a contradiction, right? So this is saying B is in the interior of this, and then but this is also right. Does this make sense?
I'm not really sure.
So this, do you understand like why this is saying B is interior to the complement of A? Because we found a radius around B that stays within the complement here, right?
Mm-hmm.
So B is interior to the complement of A. Now the interior, right? The interior of any set is like automatically open, right? So S minus A complement is, or sorry, S minus A interior is open, right? So this is open. But that means that this is closed, right? And if you just kind of visualize in your head, like since this is a subset of the complement of A, then taking the complement of that gives you a superset of A, right? So the fact that like S, that means that S minus the contains A, right? And so it's a closed set containing A, and by definition, the closure of A is the intersection of all closed sets, right? Containing A. So we assumed that B, right? That means that B is in any closed set containing A, because B was in the closure to begin with, right? So B has to be in all of the closed sets. So that means that B has to be in the complement of the interior of the complement of A. But we already showed that B is in the interior of the complement of A, and that's not allowed, right? So this is one argument. I guess maybe the 13 point, I kind of prefer this honestly, but I think maybe the 13.9c, what am I doing? Like, so by 13.9c, you could also say like, there exists a sequence in A converging to B, right? So like say AN is a sequence in A converging to B, then there exists some capital N such that for all little n greater than capital N, the distance between AN and B is less than R, right? So any AN with n greater than capital N satisfies, right? Well, I just kind of rewrote this, right? But my point is that like any AN in the sequence beyond this point can serve as like this A that we're looking for, right?
Oh, I see.
Yeah.
Okay.
So yeah, I don't know. Anyway, well, so that's kind of a lot of. I hope that answers your question. I think I'm gonna skip going through the second half of this because I think that like probably all the stuff you could need to use about the closure is like contained in this. Yeah, these ideas. Yep.
Thank you.
Mm-hmm. So any other questions before we move on to some exercises? Okay, let's see. So the next problem I had planned was, let me see. Actually, one sec. Let me hide my whiteboard for a second so I can see. Oh, I see. Okay, yeah, let's try this. So, okay, this is like a little bit of a, yeah, we'll see. So define Fn, sequence of functions on R. Yeah. By, so F0 of x is 1, F1 of x is 1 plus x, F2 of x is 1 plus x squared over 2, F3 of x is 1 plus x squared over 2 factorial, is there factorials, plus x cubed over 3 factorial, right? And so on. So these are the partial sums of the series from n equals 0 to infinity with x to the n over n factorial, right? Okay, so each of them is a polynomial. And now let's take for granted that Fn converges to e to the x pointwise on R. Does Fn, oh, this is not really how you use this. So does Fn converge to e to the x uniformly on R? That's the question. Okay. And try to like prove your answer, right? So that's the idea, is try to prove your answer here. And you can assume like any familiar like properties of the function e to the x if you want, right? Like the fact that e to the x is increasing, for example, the fact that well, that's, yeah, the fact that it's like always positive, whatever, you know, basic things like that, you can pretty much assume. All right. So yeah, I think that's a decent problem for you guys. So I'm going to go ahead, and this is, I think it's like, you know, it's kind of a substantial problem. So I'm going to go ahead and give you guys like 15 minutes to work on it. I'll make some like rooms for you guys to work in groups if you want. So let's see. I'll make like maybe two, yeah, two, three. Let's say three groups. So yeah, there we go. So yeah, we'll resume like 5:56 or 7 or so. Yeah, 5:57, I guess. Yeah. Okay, so I know this is like kind of a hard problem for, you know, it's kind of hard to do this in like a rigorous way, I guess. Uh, at least, well, again, you know, taking for granted certain things, right? We have to take for granted. Well, actually, since the answer ends up being no, so the answer is that they don't converge uniformly. You actually don't need to assume anything about whether they converge pointwise, but uh, we do still have to assume certain things about the function e to the x itself because we haven't really defined it in like a precise way. Um, but okay, anyway, uh, so here's how I want you guys to think about like. So the answer is no. Okay. So there's sort of an intuitive reason. Oops, intuition. Okay. And the intuition is that each fn is a polynomial, but e to the x is exponential. So e to the x, like for any given n, e to the x eventually outruns fn of x. Okay. So here's how I would like try to go about, you know, giving like a real, you know, sort of rigorous solution to this problem. And it would be, so I would basically first say like, as a lemma, we claim that the limit as x approaches infinity of e to the x over fn of x is infinity for each n. Okay. And so to show this, basically what you can do is say like, okay, first note that, let's see how to say this. So I want this to be bigger than something. So to make it smaller, make the denominator bigger and the numerator smaller. So yeah, like e to the n over like, or n is kind of like yeah, let's say k here. So e to the k over like f n of k plus 1, the limit as k approaches infinity, where k is like a natural number, right? So this forms a sequence, okay? And this is infinity. This is just by like, okay. Because, so we can do this because, so fn of k plus 1 is a polynomial in k. And actually what we can say is that it's like, it's a polynomial with like all positive coefficients. So basically fn of k plus 1 is like, let's say, bigger, smaller than, right? It's smaller than something, which means that the overall thing is bigger. Right. So fn of k plus 1 is like less than or equal to like ck to the, and it's a polynomial of degree, like degree n, right? So ck to the n for some constant c, okay? Are you guys, are there any questions so far? I know I'm kind of like, I know these are like big, kind of big steps right now. So like the reason, right? So, okay, like fn of k plus 1 is just like 1 plus k plus 1 plus like k plus 1 squared over 2 factorial plus, right, all the way up to like k plus 1 to the n over n factorial, right? And so what I'm saying is like, this is, you know, this is like, if you distribute, you know, you get some kind of like a, you know, 0 plus like a 1k plus, you know, a 2k squared plus like a n k to the n, right? And then you can say like this is less than or equal to, since all, you know, all the variables are, or like, I don't know, not variables, but like all the like a, j's, and like k are greater than or equal to 0. This is less than or equal to like, you know, an, like, or like maximum of like all the aj's times like k to the n, right? So if you just call this c, so there's some constant times k to the n, right? That fn of k plus 1 is like less than or equal to this. And then what we can say is like, so the limit, we know that the limit of like e to the k over c k to the n is infinity by like, this is like just from section, there's some theorems in section 9 that'll give this to us. So let's see. I think it's like, where is it? Well, I mean, right. Okay, we've seen this before, right? Like you can do like the root test on this or something, right? So like the kth root of like e to the k over c k to the n, right? Approaches like e, right? So that tells us, that basically tells us that that this approaches infinity. Does that make sense to you guys?
Would it be e over kth root of c? Or no.
Yeah. So you'd have like, it equals, right? I'm saying it, so it equals, precisely, it equals like e over c to the 1 over k, and then like k to the n over k, right? But we know that like k to the n over k, I mean, this is just k to the 1 over k to the n. And we know that this approaches 1, right? And this approaches 1. So this overall thing approaches e, okay? So yeah, it's not too hard to get from here. Like one thing you can actually do is just say like 1 over this, right? Like this, the actual, by the root test, this says that like the sum of like ck to the n over e to the k converges by the root test. So like ck to the n over e to the k goes to 0. So, so e to the k over ck to the n goes to infinity, right? So, okay, yeah, it's a little bit convoluted, but there might be like an easier way of doing this. There's actually an exercise. So there's an exercise in section 9, 9.14. So see 9. Like exercise 9.14. Okay, that you can look at if you want to like really explore these ideas. So and this also, like, I'm pretty sure I actually assigned 9.12. So yeah, 9.12. So 9.12 was on a homework, and then 9.14, which is basically exactly what I'm talking about right now, that follows from 9.12 basically. Yeah, it's like it's actually not that hard. Oh yeah, in that one they use like the ratio test, right? Okay. Anyway, sorry. So sorry, this is getting a little bit convoluted, but anyway, so basically what we've shown, all right. So to take stock of what I've said so far, is that the limit, this limit of e to the k over fn of k plus 1 is infinity, right? So let's continue from that point. So we've shown that the limit as k approaches infinity of e to the k over fn of k plus 1 is infinity. Okay, now for any xn with xn going to infinity, note that if k, let's say, oh, I shouldn't use n. Let's say like xj, right? If kj is like the floor, so say like kj is the floor of xj, and yeah. Then like e to the kj is less than or equal to the e to the xj, and like fn of kj plus 1 is greater than or equal to fn of xj. So let's see. That means that, so e to the x over fn of x plus, or fn of x, sorry. E to the x over fn of x, right. xj, sorry. This is greater than or equal to, oh, did I flip these around? Oh, no, this is right. Yeah. E to the kj over fn of kj plus 1. Right, and then this goes to infinity. So this also goes to infinity. That's the point, right? So remember, the whole thing I was trying to show was just this fact, right? So let's call this like, well, this is the lemma, right? So this proves the lemma. So are there any questions so far? I know this is like a complicated thing. So the whole point of this, like the whole reason I was even looking at these sequences and stuff, is because like we have theorems, right? Okay, so we have theorems that tell us that like an exponentially growing sequence grows faster than like a polynomial sequence, right? So what I'm trying to do is I'm trying to show, like, we don't actually have a theorem that directly tells us that an exponential continuous function grows faster than like a polynomial continuous function. So all I'm trying to do is basically relate these like functions of a continuous real variable to these like corresponding sequences. So I'm saying like, okay, since they're both like increasing, right? So all I can do is look at like a nearby, if I take a random sequence, right? If I take like a random sequence of xj's, these xj's could be like, who knows what kinds of numbers, like they could just be random real numbers that approach infinity. But the point is that like for each one of these xj's, I can find an integer. I can actually find like an integer nearby, at least for positive integers, like, so without loss of generality, assume that like the floor of xj, or just assume that like xj is like greater than or equal to 0, right? Because like if xj approaches infinity, then I can just like cut off the beginning of the sequence to make them all non-negative. So if they're all non-negative, then like by looking at like nearby integers, I can basically compare the values of like e to the xj over fn of xj. I can compare it to these like values where I use nearby integers, basically, right? And then I already know that as a sequence, like this has to approach infinity because this is just a subsequence of the e to the k over fn of k plus 1, right? So this approaches infinity, so this approaches infinity. And since xj was an arbitrary sequence, right, approaching infinity, then that shows that that e to the x over fn of x goes to infinity, okay? So now we've established the lemma. And now it's actually pretty easy. So then what we can say is like, okay, so let epsilon be greater than 0, right? Then, or sorry, not let epsilon be greater than 0. What am I doing? Yeah, like pick, I don't know, pick epsilon equals like 1 or something, right? Then let n, what I'm going to do is show that we can find an x such that like, so then there exists an x such that like e to the x over fn of x is greater than like 2, let's say, right? And also choose this x such that like fn of x is greater than 1, right? So then e to the x minus fn of x, let's see, this is like this is greater than like 2 fn of x minus fn of x, which equals fn of x, which is greater than 1, right? So the point is, so fn of x minus e to the x is greater than epsilon for this x. So the point of all of this is that like, no matter what n is, no matter how big n is, I can always find a value of x somewhere so that the distance between like the limiting function e to the x and fn of x is bigger than this particular epsilon that I picked arbitrarily. I mean, you could pick any epsilon you want. I just picked epsilon equals 1 because it's the simplest one. But yeah, you can basically make this argument and show that like there's no capital N for this epsilon that makes the sequence stay uniformly close to e to the x. Okay? So any questions about that?
I have a question.
Uh-huh.
Where did the 2 come from?
This was just to make this like work out simply,
okay.
I guess. Yeah, I mean, like, so I picked this, like, I basically picked that like arbitrarily. So
okay.
yeah, I picked 2 just to make this work out. Yeah. But you can mess with a lot of the constants here. Like, I mean, you could make this be like, as long as this is anything strictly bigger than 1, I think. So like anything greater than 1 will work. Yeah.
Right, okay. I also have another question, if that's okay.
Yeah, sure.
So in chapter 24, there's a remark that says, it's remark 24.4. Can you please explain a little bit? I'm not sure if I understand it completely because, okay, yeah, that's it, yeah.
Oh, sure. Yeah, the point is like, okay. So basically, okay, so remark 24.4. Actually, okay, sorry. Before I get into this, I will explain that in a sec. I want to just recap. I want to recap this whole idea here, this whole proof here that I just did a little bit, because I feel like there's a lot of annoying technical stuff. Like this whole thing here is like very just like technical, and so I want to just outline the major ideas that were here, right? Or yeah, like the major ideas, right? Which are, so the major ideas of the proof, right? If, so like, obviously the lemma is one of the major ideas, right? So we were saying like e to the x over any polynomial goes to infinity, at least if the polynomial stays greater than 0, you know, asymptotically, which obviously is the case here, right? Because the polynomial we were looking at, like the polynomial we were looking, all the polynomials we were looking at had positive coefficients, right? So these polynomials, they're like polynomials that grow towards positive infinity. And the whole point is just that like e to the x just grows faster than any polynomial, right? So like, that's kind of like the spirit of this. So e to the x grows faster than any polynomial, right? So there's that. Okay, that's one of the ideas. Another idea is that like, okay, if e to the x over anything over fn of x, let's say, is a large positive number, then like e to the x minus fn of x is large too, at least as long as like fn of x itself is also large, right? So we know, it's like we know two things at the same time, right? One of the things we know is like fn of x goes to infinity, right? As x goes to infinity. This is all as x goes to infinity, right? So as x goes to infinity, fn of x is growing, but at the same time, like eventually, like once you get to like large enough values of x, e to the x over fn of x is also getting really big, right? So then it's like clearly the distance between them has to get like bigger and bigger, and basically it has to go to infinity, right? So so like the whole point is just like these things together mean that fn cannot stay uniformly close to e to the x. In fact, now that I think about it, there might be an even easier argument. Like once you, let's see, once you show this much, once you show the lemma, it might be even easier to prove the final result, just because you can say like, if fn of x minus e to the x were like less than epsilon for all x, then it would be easy. Then it's like easy to show that the limit as x goes to infinity of like e to the x over, or let's say fn of x over e to the x is 1, because we would know that like fn of x minus epsilon over e to the x is like less than or equal to or sorry, e to the x. Dang it. Yeah, e to the x. E to the x, and then we'd have like fn of x over e to the x less than or equal to e to the x plus epsilon over e to the x, right? But this is just like 1 plus or 1 minus epsilon over e to the x, and then this is like 1 plus epsilon over e to the x. These both like clearly approach 1, right? So then this is kind of squeezed in between. So this would approach 1 by a continuous version of the squeeze lemma, which is very easy to show. If you already have the sequential squeeze lemma, right, then you can just like basically automatically convert that into like a continuous squeeze lemma. So that would just directly contradict what we showed before, which was that e to the x over fn of x approaches infinity, right? Or alternatively, that fn of x over e to the x should approach 0, okay? So this is actually, in fact, this is, I think, maybe an even better way of using the lemma to like finish off the entire proof. Does that make sense? Are there any questions about that? But yeah, I at the very least, I hope that like these major ideas kind of like help you, because again, it's like this is like a very classic example of a fact that is like intuitively pretty easy to understand, but the proof ends up being really annoying and complicated. And the whole skill here is like taking your intuitive ideas and converting them into like rigorous arguments. So like this whole business, honestly, I just like made this up pretty much like right now. So I don't know, there might be a better way of doing this too. To show, right? Because like I was saying, I was doing this to like cope with the fact that that like we're trying to prove something about a continuous limit here, and all we really have to work with is stuff that we know about sequences. So, yeah, I don't know. Anyway, yeah. So let me try to like clarify this thing about this 24.4. Right. Did I already? Okay. So so they're just saying, so Fn goes to F uniformly on S. If and only if the limit as n approaches infinity of the supremum of f of x minus fn of x for x in S equals 0, right? So the whole point of this is just saying, like, normally we say, like, for each epsilon greater than 0, like, the distance between like f of x and fn of x is less than epsilon for all x and sufficiently large n, right? This is a way of phrasing, like phrasing the normal definition of uniform convergence. This would be like a colloquial way of saying that, which is just saying that, like, yeah, for whatever epsilon you want, you can like pick a big enough n value that like fn of x is within epsilon away from f of x for all x values, right? And this one is just saying that, like, the furthest distance between fn and f on S is less than epsilon for sufficiently large n, right? And so it's kind of like, in translating between these, all you're doing is just saying that, like, you know, to go from, to like, to infer this one, to infer the normal definition from the weirder definition, all you're just saying is, like, if you assume that the furthest distance, right? And when I say furthest distance, right, I'm not being very careful, because obviously, since this is a supremum, it's possible that it's like just the least upper bound on these distances, but there's not actually a point in S where the distance is equal to the supremum. But it's okay, because it's like, you can get really close, so it doesn't matter, right? So I'm just going to call it the furthest distance, even though it's like not really the furthest distance. So all I'm saying is, like, if the furthest distance between F and Fn across all of S, right, is less than epsilon, then clearly the distance itself at each point in S is less than epsilon, right? Because if the furthest one is, then all of them are, right? The biggest distance is less than epsilon, then all the distances are less than epsilon for every x value, right? So that's one thing. So that's kind of how you go from here to here. But then going from here to here, all you have to say is, like, okay, if the distance between f of x and fn of x is less than epsilon for every single x, then, like, the supremum of all of those distances across all the x values, right, since it's the least upper bound, this is saying that epsilon is an upper bound, right? Epsilon is an upper bound on the distances between f of x and fn of x. If epsilon is an upper bound, then the supremum is less than or equal to epsilon, right? But then the fact that, like, the supremum, you can make the supremum be less than or equal to epsilon for any epsilon, that shows you that the supremum has to go to 0 as n gets large. Okay. Does that help?
It does help, but this seems kind of like a stupid question, but this is not lim sup, or this is...
No, yeah, no, it's not a lim sup. This is like literally a limit, right, of a bunch of suprema of, like, these weird, yeah, these things.
Okay.
So this is just a sequence of numbers.
I see.
Mm-hmm.
Okay, thank you.
Yeah. Yeah, like, all we're saying is, it's like, you know, the supremum of f of x minus fn of x for x in S. I'm calling that, like, the furthest distance between f and fn on S, right? And so, like, fn, as fn varies, like, that furthest distance is going to change. So you get a sequence, you get like a sequence of numbers that way. So they form a sequence of numbers. Okay. So one more thing about this kind of nightmare problem here, which, by the way, like, okay, I'm not gonna assign something with a solution like as involved as this one, probably. Okay, at least not without a little bit of guidance, just to be clear. But you shouldn't take this as an indication of like how difficult the exam itself is going to be. The real point of this is that I think, like, you know, it combines a lot of the important concepts that I am going to be asking stuff about, and it tests your like feeling for them. So, but okay, so the answer here was no. What we showed is that this does not converge uniformly on all of R. But what if instead of R, we replace this with like a closed interval? Okay. So does Fn converge to F uniformly on, let's say, AB, right? Just as a yes or no answer, what do you guys think? And these, again, are being taken from the previous problem. Does it converge uniformly or no? In fact, let's make this even a little bit easier, or a little bit more like, I don't know, a little bit simpler to think about. Just like negative R, R.
I think the answer is yes.
Okay. Do you have any sort of intuitive explanation of why?
My intuition is you can choose the like largest x.
Mm-hmm. Yeah.
And
That's
okay.
yeah. That's one way of thinking about it. Yeah. I mean, that's the right way of thinking about it, I think. Another way of seeing like why we should expect it to converge uniformly is that, like, in this problem, like, as n gets bigger and bigger, right? The point is that here, let's see. Right. Here, what we were doing is like we're choosing an x value for each fn such that like e to the x is far away from fn, basically, right? And so that x that we pick, it depends on the n value, right? Because the thing is that, like, as n gets bigger and bigger, you have to go farther and farther out to find a place where e to the x is far away from fn of x. And so, like, these x values, as n gets bigger and bigger, these x values have to get like bigger and bigger, and they end up kind of approaching infinity, actually. Like, how large you are forced to make x gets like arbitrarily big, basically. So because of that, if you limit x to being from like a finite interval, then eventually for large n values, you're not going to be able to go far enough out. You're not going to be able to pick a big enough x value to like make this distance get large, basically, like we did here, right? To make this happen, you won't be able to pick the x value that you need because it'll be too big. It'll be outside of the interval. So that's another way of thinking about it. But yeah, you can actually like prove this very easily with what one theorem?
The M test?
Yeah, exactly. Yeah. So so apply the Weierstrass M test with, so we would have like gk of x is like x to the k over k factorial, right? Then gk of x is less than or equal to r to the k over k factorial on negative r, right? So the sum of, and so like if you set this to be like mk, that's just like e to the r, right? Which converges. So this sum converges. So since it converges, then right. Yeah. And this logic here is exactly what we were saying about like looking at the biggest x values kind of, or just basically looking at like where it's kind of looking at like where do we expect the error between fn and f to be greatest. Implicitly, that's what's happening. Is that we're basically like dancing around the fact that there's like an upper bound on how far away they can be from each other because we're just like limiting our attention to this finite interval, basically. Yeah. Okay. So cool. Any other questions? So for example, like now with this, what we've just shown, under the assumption that, at least under the assumption that that fn converges to e to the x pointwise on R, what we just showed actually shows that e to the x is a continuous function on all of R. Because if you want to show that e to the x is continuous at any specific point in R, you just pick some big enough interval and then invoke the uniform convergence on that interval to say that like the point that you picked, e to the x is continuous at that point. So that's like one nice side effect of this whole, of this thing here. Even though the convergence is not uniform like on all of R simultaneously, you can still kind of like get around that and show that e to the x is continuous everywhere. Okay, anyway, so I have a couple more questions that are easier than this one, to be clear. Let's see. So yeah, maybe. Oh, what? Okay. How about hmm. Which one was it? Okay. Yeah, so maybe this. So show that if fn converges to f and gn converges to g uniformly on S, then fn plus gn converges to f plus g uniformly on S, but not necessarily. So these are separate two things. Hold on. Okay. That's like, but one can arrange for Fn Gn not to converge uniformly to Fg on S. Okay, so like the first part is just doing a general proof that this is true for all possible pairs of sequences, right? And then the second part is coming up with a counterexample. And if you already looked, so this is kind of based on some exercises from section 24. So you might have already seen a counterexample in there, but if you already saw the counterexample, then at least like try to go through the proof of why it works as a counterexample. Otherwise, I would encourage you to try to think about, try to think for yourself about what a counterexample would be. And then also kind of like think about how, like what extra conditions basically, what extra conditions would force Fn Gn to converge to Fg uniformly on S. Okay, so let's say we'll resume again in like 10 minutes. So 6:50, 6:54, let's say. Okay. Yeah, this one, it shouldn't be too long to explain, I think so. Let me open the rooms here. All right. All right, so let's see. So for part A, there's like a name for the type of argument that we'll make here, and we've seen it before, right? What argument? What's the name of this like argument? If you guys know.
The epsilon over 2 argument.
Yeah. So this is just another epsilon over 2 argument. Right. So pick n such that like fn minus f is less than epsilon over 2 on s, and gn minus g is less than epsilon over 2 on s, right? And this is, of course, you can pick separate n's for each of these conditions and then like pick the maximum of those, right? So that's how you get this capital N. Then for n greater than capital N, fn plus gn minus f minus g is less than or equal to fn minus f plus gn minus g, just a triangle inequality. And then this is like less than epsilon, right? So hopefully, like, the point I'm trying to make here in being so sort of like cavalier about this is that like hopefully by now you've kind of like seen this argument enough and you have enough of a sense for like the structure of how these proofs work that you can almost see this entire proof kind of like playing out in your head in a way, like just when you look at the statement. And it's like something that basically like this statement here, just the first statement overall, if you just saw that, like hopefully you'd kind of look at that and be like, yeah, not only is that like a reasonable thing to believe, but I do actually believe that this should be true. Because you can kind of like in your head, you can just be like, oh yeah, epsilon over 2. There's no reason the epsilon over 2 argument wouldn't work here. It's just that now we're using the epsilon over 2 argument with like an extra x variable floating around, but like whatever, it doesn't matter, right? Now, this here is when things get wonky, right? So I'm just gonna, since I know like, you know, some of you, maybe all of you might have already seen the counterexample in the book, so I'm just gonna go ahead and state it. So so say like S is just all of R, and then like Fn of X is just X for all N, and then Gn of X is 1 over N, right? Constant. So then like clearly Fn approaches F. So like F of X would just be X, right? It's literally, Fn is just like a constant sequence because each function is the same. So this, any constant sequence obviously converges uniformly because Fn minus F of X, Fn of X minus F of X is just always 0 for every X value. So this is uniformly, and G of X would be 0. So like Gn approaches G uniformly. This is also not hard to show, like given epsilon greater than 0, pick capital N such that, well, just pick capital N equals 1 over epsilon. Okay, so yeah, then Gn minus G absolute value is going to be 1 over N, which is less than epsilon for all X because it's just a constant. So yeah, so we have that, but Fn Gn is of X is X over N, right? And Fg of X is 0. And we've actually seen, so I believe I assigned this as a homework problem, right? That x over n does not converge to 0 uniformly. Well, it's like the convergence is not uniform. Right, and hopefully that also makes sense, because if you just think about it, like all you have to do is, if you take like epsilon equals 1, for example, then for any n, if you just pick x to be bigger than n, then fn gn of x is going to be bigger than 1, even though fg of x is 0, right? So yeah, this definitely doesn't converge uniformly. Any questions so far? Did you guys have any other like different counterexamples? So I would say that like the key thing that kind of pops out about the counterexample here is the fact that like one of these sort of converges to this like random function, and then the other one converges to 0. And it's especially the 0 that I think like really makes this work. And I actually haven't fully thought this through, but my suspicion is, and this is sort of getting at the last thing that I talked about, which is like what other conditions might work. So I suspect that if we say fn converges to f uniformly on S, gn converges to g uniformly on S, and like let's say like there exists like m1 and like m2 such that like fn of x, or sorry, m1 like greater than 0, m2 greater than 0, such that f of x is like greater than or equal to m1 on S, g of x is greater than or equal to m2 on S, then probably fn gn converges to fg uniformly. I think, I don't know. My instinct is that this would be enough. You might even be able to relax these. So it might be possible to relax these conditions too. So this might actually be too strong. Like maybe it's actually enough just to require f and g to be like strictly positive, which is different, right? So like for example, what if we just require f greater than 0, g greater than 0, right? I'm not sure. Things could get pretty dicey in this situation, but here I definitely feel like we're safe if this is true with these M1 and M2. And oh man, I'm actually out of I'm out of new pages on the whiteboard. What the hell? Zoo, why would you it limits me to like 20 slides on the or pages or whatever. All right. Well, so I think what I would say is just like for this part, if you remember like so I kind of went through like multiple different proofs of this. But when we were looking at just sequences of numbers, right? And we were looking at products, like the product of two sequences of numbers, where the limits, well, yeah, there was some boundedness conditions on them or whatever. But the theorem about limits of products, right, used like this inequality that was like an bn minus ab is like less than or equal to, and then you add in like an b and like A and B in the middle or something, and then use the triangle inequality. So like something like Fn Gn minus Fg is like less than or equal to like Fn Gn minus like Fgn plus like Fgn minus Fg. And then this is like, okay, Fn minus F times Gn. Oh, I see. Then maybe, oh, maybe actually you have to be able to bound them both. Yeah, I guess it's actually the fact that like also this is unbounded. So actually, okay. Yeah, it's like the combination of those things. So maybe actually if you just say, in fact, this might not even be necessary. This might be the wrong thing. F and G are bounded on S. That would be enough, I think, right? So then like, okay, plus, this is like plus F times like, yeah, and then like Gn minus G. So you can basically bound both of these two things. And then you can force these things to be like small. And that's how you do it, I think. Well, anyway, whatever. It's not a big deal. So yeah, sorry. So this is, I think this is actually wrong. Just goes to show you can never be too careful. So it's good to be careful and actually think through your arguments and stuff. Okay, anyway, well, that's it. That's all for the review, unless there are any last minute questions. Okay. Yep. The exam will go live at midnight, and it's going to be like the same format, you know. So, all right. Good luck, everyone.
Thanks. Bye.
Mm-hmm.